Okay, well, welcome back. We continue on with the kinetic theory and discovering solids, liquids, and gases. Probably in elementary school, when they talked about solids, liquids, and gases, they didn't tell you that there's really two different kinds of solids. The first kind of solid is called a crystalline solid, and its name tells us exactly what it is. It's a solid made from a regular repeating pattern of particles. Now that regular repeating pattern is it repeats over and over and over. Each little molecule that builds on one, they're all identical, but they're making this little pattern. And that pattern, as it repeats, is what makes the crystal. Okay? They have an exact or definite melting point. And what that means is there's a temperature. When you raise their temperature, they get to one point, and 1 degree up, they're going to be a liquid. 1 degree down, they're a solid. It's at that exact point where they're going to change from a solid to a liquid. And we're going to talk about what that's different in some other solids. So examples of some crystalline solids are ice, diamond, and salt. And I included this little chart that shows the melting point of some of these crystalline solids. So here's NaCl. This is regular table salt. It shows us it has a melting point of 801 degrees. So at 800, it's a solid. At 802, it's a liquid. At 801 is the temperature, the exact temperature that it melts at. And here's diamond. Diamond melts at 3,500 degrees. So that's the exact melting point at which the diamond will go from being a solid to a liquid. This one, SiO2, is silicon dioxide. That's basically what sand is made out of. Okay, and again, it's got this exact melting point. It's the temperature, which is going to go from a solid to a liquid. And here's one that we're really familiar with, water. Water, H2O, down at the bottom, and it's going to melt at 0 degrees. So at -1, it's a solid. 0, it's changing from solid to liquid. And at 1 degrees, it's a liquid. Okay. The other kind of solid is called amorphous. These solids do not have that crystalline repeating pattern. They also do not have a specific melting point. When we heat them, they get softer and softer, and then they finally turn into a liquid. So it's not like these, like with the water. With the water, okay, the ice is a solid, and then it's a liquid. There's no point at which an ice cube is kind of soft and mushy. Now, many of these amorphous solids are delicious to eat. So example, ice cream, chocolate, butter, and wax, all examples of amorphous solids. So if you think about ice cream, it was in the refrigerator and it was really, really frozen. When you pull it out, it's so hard you can't even get a scooper in it. If you let it sit out for a little bit, it's still a solid. It has a definite shape and a definite volume, but now it's soft enough that you can scoop it, and it's probably better to eat that way. The same thing with chocolate, butter, wax also gets soft like that. I made this little slideshow so we can take a look at some different amorphous and crystalline solids. Okay, so here we have some examples of crystalline solids. And you can see how they form these regular repeating patterns. Whether it's a small crystal or a larger sample of the crystal, they all have the same size. That's because each molecule is a small crystal, and then they bond together, and they, in the same pattern, and make bigger and bigger crystals. Okay. Now this wax is an amorphous solid. Okay, here where it's dripping and it's cooled a little bit, it's probably soft and moldable, but it's still a solid. It's got a definite shape and it's got a definite volume, but you can change its shape. It's at that in-between point, and right down here you can see the drop is a liquid. This is another example of a crystalline solid, and you can see whether it's big crystals in here or little crystals. It forms this regular repeating pattern, And this substance would have an exact melting point, a temperature at which it would change from being a solid directly into a liquid without getting soft. Now this chocolate is an amorphous solid. So we can take a look at it, and you know how chocolate is. If it's nice and cool, it'll snap and break. It's very solid. But if you get it, out and it's a little warm, it gets to that point where it's soft, but it's still, it's a solid. It gives definite shape, definite volume, but it is soft and, moldable. Same thing with this glass, okay? It is not yet a liquid, but it's soft enough this glass blower can change its shape. So it would be another example of an amorphous solid. It hasn't gone directly from a solid to a liquid. It has this point in between where it's getting softer and softer. Here's some other examples of some crystalline solids. Okay. This ice cream picture is a really good one, and I like this because it shows the chocolate is still at that point where it's hard and it's brittle. It's cold enough. But the ice cream inside, you can see, is at that point where it's getting softer and softer, okay, but it's still holding its shape. So it has a definite shape, a definite volume. It hasn't turned into a liquid yet where it's going to run out. But when you look at the picture, you can tell it's soft. Okay, so as we said with the amorphous solids, they don't just transition. They have a point where they're soft, and then finally they turn into a liquid. Here also with this butter, you can see the same thing. It is still a solid. It has a definite shape and a definite volume. It's got the shape of the cube. But you can tell also it's at that point in between where it gets softer and softer before, if you heat it, eventually it would be a liquid. Here's some examples of the crystal lattices that these crystalline solids form. So we saw some that are cubes, some that are hexagon, and these are the individual molecules. And as these molecules hook to one another, they make bigger and bigger crystals. Now, we started off with that solid where all the particles were bonded together and there were springs holding each one. And we said those springs represent the connections between the particles. And as the particles are cold, they're not vibrating very fast. And as they get heated, they vibrate faster and faster and faster. Well, as they go faster and faster and faster, they're starting to bounce out away from each other farther and farther. Eventually, they bounce so far that they break that connection that was between them. When that happens and the connections start to break down, that's when the phase change happens. That's when they're going to be going from a solid to a liquid. We say that liquids have no definite shape, but a definite volume. So you know, for example, if you pour water from one container to another, it'll take the shape of its container, but the amount of water does not change. The volume doesn't change. Okay? Because they're not completely connected to each other like in a solid, the particles are said to slide past one another. As they can slide past one another and they're not all connected, okay, they will take the shape of their containers. So as I just explained, the particles are vibrating fast enough to overcome the ordered arrangement, the bonds that were holding them together to make them to be a solid. So here, I put some liquid particles in this container, and some of the bonds are broken, okay? Before it became a liquid, they were all hooked together in that nice orderly pattern. Every single one of them was connected. But now you can see that they're still connected in some way. They're not free to move around like they will be when they're a gas, but they're not as connected and ordered as they were when they were a solid. Okay. The melting point is the point at which the solid will change into a liquid. So we said that's that point where those particles are starting to vibrate fast enough that they're moving farther and farther away from each other as they gain energy, and they're vibrating farther and farther. And that's also what's causing the thermal expansion, because they're moving farther away from each other. So eventually they move so far away, some of the connections break. So this solid at which a solid changes to a liquid. And that energy that's necessary to break those bonds down so that it becomes a liquid is called the heat of fusion. Viscosity is the resistance of a liquid to flowing or pouring. So I made this little chart so we can put some liquids on here. For example, syrup is very viscous. So water, it doesn't have much viscosity. It's kind of down here on the low end. Milk is a little bit more viscous. It pours a little bit more slowly. Honey is very viscous. It pours very slowly. Oil, depending on whether it's cooking oil or vegetable oil, is more viscous than milk but less than honey. Rubbing alcohol pours even easier than water. And syrup is more viscous than oil, but it's usually not as thick as honey. I'm going to show you a small video on viscosity, and then we'll pick up with this tomorrow. All right, just a little video that I wanted to show you on viscosity. Well, you can see here they have some different liquids: vegetable oil, honey, syrup, Dawn, motor oil. They're going to put each of those liquids in this graduated cylinder, and then they're going to drop a marble into the graduated cylinder. And the slower it sinks to the bottom, the more viscous the liquid is, or the more resistance to flow it has. So they have the vegetable oil in the graduated cylinder. The marble sinks pretty quickly to the bottom, so it's not that viscous compared to motor oil. Okay, motor oil is more viscous. It took longer for the marble to sink to the bottom. Okay, the dish soap is even more viscous. Marble takes quite a bit longer to sink to the bottom. The syrup is very viscous. You can see how slowly the marble is settling to the bottom. And then finally, the honey. Look at the viscosity of the honey. It sinks very, very slowly. They're going to try it with a larger marble to see how the more resistance to the flow. And with the larger marbles, you can see the difference in the viscosity quite a bit. The dish soap and the syrup and the honey, the marble is moving very slowly, so you can get a pretty accurate measure of the viscosity.